All right. Before I introduce our speaker, I want to acknowledge that the University of Washington sits on the traditional lands of the Duwamish people, most of whom are now members of the Muckleshoot Nation. Today, we are graced with the presence live in person of Mohit Melwani Daswani from the Jet Propulsion Laboratory. Mohit began his career in Spain before moving on to the Open University in the UK, where he obtained his, oh wait, nope, I forgot one. You did the Erasmus Mundus program across Europe, which is a fascinating program where you move around Europe to multiple different institutions and you get your master's degree. From there, he went to the Open University in the UK for his PhD. He then decided to come to this side of the pond, and he had a postdoc with Edwin Kite at the University of Chicago. Then he went to JPL, where he is now, but he started there as a postdoc with Steve Vance, who some of you know is a alumnus of this program. And then he's recently been transformed into a senior scientist at JPL. So today he's going to be talking to us about the interiors and evolutions of some of the icy satellites and worlds in our solar system. So please take it away.
Thank you, Rory, and thank you for the opportunity, and thanks for coming along and to listen to this talk. So yes, first I should acknowledge that this work was done in collaboration with a lot of collaborators. Matt Main from Stellenbosch University, Chris Lyon, who you will get to know soon enough if you don't know him already, Steve Vance, as Rory mentioned, and Julie Castillo-Roges has helped out a lot on the work relating to Ceres. So the topic of today's talk is metamorphic origins for the oceans of Europa and Ceres. So we've essentially tested a hypothesis as to the origin of oceans on ocean worlds, and we looked at Europa specifically because we were funded to do so. But then we've expanded our interest to looking at Ceres, because Ceres is a bit of an odd object in the inner solar system. It's the only dwarf planet in the inner solar system, and it has a relatively low density. So we are not quite sure what Ceres is made of. We have some spacecraft observations and some ideas. And so we're testing out several methods to get Ceres to look like it does from a theoretical standpoint. So the Europa work is already published. We published it in just earlier this year, Geophysical Research Letters. So I welcome you to check that work out. And I should also mention that I received a lot of help from student interns, Andrew Chan from Caltech and Jack Dia from Southern Oregon University. So, so the talk is mainly structured this way. I'll talk a bit about the motivation of this work. Specifically, I'll look at this matrix that we came up with to motivate the work, where we tried to relate tidal dissipation with habitability. Is there a relationship between tidal dissipation in Europa and habitability over time? This is something we looked at it from a qualitative perspective, but we're trying to put actual numbers to this. Then I'll just introduce some of the ocean worlds. You're probably quite familiar with some of them in our own solar system. And then I'll talk about the results, specifically for Europa in the first half, and then Ceres in the latter half. So this is the matrix I mentioned before. So this qualitative matrix was sort of a back of the envelope thing we came up with about 3 years ago now. We wanted to understand whether fluxes of energy and mass within Europa could sustain life within Europa, life as we know it. So on the y-axis, you have increasing heat from the bottom to the top. And on the x-axis, you have increasing time from left to right. So this sort of not very exhaustive or really crude matrix just shows possible outcomes for what tidal energy can do to sustain life, or perhaps enable its death. So we were thinking of, well, if Europa, and Europa is tidally locked in orbiting around Jupiter during times when it returns from high eccentricity to low eccentricity, it experiences high tidal dissipation. That means that friction within Europa ends up heating the body, perhaps maintaining the liquid water ocean that we know of today, perhaps heating the rocks in the interior, and maybe causing fluxes of redox sensitive elements or what have you between the ocean and the rocky interior. So imagining that maybe there's no heating in the interior, then you reach a point of thermodynamic death. You just reach equilibrium, chemical equilibrium. And chemical equilibrium is pretty bad for life. If you're in chemical equilibrium, you're dead. So this is a scenario we would like to try to avoid if we're some form of life form within Europa's ocean. At the other end of the spectrum, if you have high amounts of tidal heating, perhaps you reach a case where the interior silicates melt and you have perhaps volcanism. And at that extreme end, if you have a lot of volcanism over hundreds of millions of years, perhaps you reach a case in which you get rid of the ice shell and the ocean and you end up like Io. So Io is the most volcanically active object in our solar system. And we don't think it's particularly habitable. It has vigorous magnetism and has no hydrosphere to speak of. And so in between these end member scenarios, you get different scenarios where perhaps you can sustain life, perhaps you can sustain life through during punctuated points in time, or perhaps in sort of these Goldilocks zones, perhaps you can have sufficient energy and nutrients, or a nutrient flux and energy to sustain life as we know it. But this was just the qualitative matrix, and we are trying to put actual numbers to this. All right, so that was the motivation. Let's talk about ocean worlds within our solar system. So last week, I think you had a presentation by Alyssa Roden, who also gave a little bit of an introduction to ocean worlds, and specifically some of the ocean worlds around Jupiter, I think. So this figure here just puts some of the ocean worlds that we know of, or that we think are ocean worlds within our own solar system in some sort of context. So we have radius on the x-axis and density on the y-axis. And what you'll find is that Europa, which we think of as an ocean world, is quite dense. It's comparable to our dry moon and comparable to Io, which we consider rocky satellites. Ceres, on the other hand, is comparable to other known icy bodies within our solar system, with a relatively low density, low bulk density, and a relatively small radius. And so more or less, we think that Ceres has if we just look at the density, Ceres might have a comparable amount of water to large icy satellites, which we do think have quite a bit of water. And so the way we thought about this was, well, what are these planetary bodies actually made of? And so we were looking at materials within our own solar system that contain large amounts of water, but not necessarily as ice. So we find that carbonaceous chondrites themselves contain quite a high concentration of volatile elements, including water, in the mineralogy. So CI chondrites contain about 28% water. If you take all the clay minerals within the CI chondrites and you just took out the volatile elements, so namely the clay minerals contain a lot of structural water and hydroxyl groups. CM chondrites are also carbonaceous chondrites. They contain large amounts of carbon, as well as water, and mainly the water is locked up in the mineral serpentine. And so serpentine contains about 13 weight% water. So we know from spacecraft observations and from Doppler measurements from terrestrial radar, actually it's from the Deep Space Network, we know that Europa is a differentiated body, meaning that it contains a metallic core and a low density exterior. And Europa contains perhaps around 10 weight% water, maybe 8 to 12 weight% water. And so that falls between what we know from meteorites. So meteorites may contain more water than Europa on the whole, or less water than Europa on the whole. So sort of naively, you can think that Europa might be formed from these meteorites. And then perhaps its ocean is a product of what is already in the meteorites. You don't need to invoke extra ice or water from some external source. So these are some of the ocean worlds in context. And I'll just point out some of the things I already spoke about. So on the bottom left, we have Europa. By the way, this is not to scale. This is just a graph to show what we think these ocean worlds might look like and what their structures are like. So Europa over here has a pretty thick hydrosphere, including its ice shell, and metallic core, which is probably made of iron or some sort of iron sulfide alloy, and then a rocky interior of relatively high density. For Ceres, I'm sorry, that's sort of blocked off there. You can't really see what's going on over here, but overall, Ceres is a bit of a mysterious object. So it has a relatively low density mantle of somewhere between, oh, there it is, 2,400 to 2,800 kilograms per cubic meter. And so we don't really think of Ceres as being completely dehydrated in the interior. There must be some sort of low density phase in its interior, causing it to be overall of low density. And we think that the crust of Ceres is another low density material, possibly containing a lot of locked up ice or clathrates. And so that overlies or lies on top of the mantle in Ceres. But we don't think Ceres is completely differentiated, differentiated as Europa is. So it doesn't have, or we don't think it has, a metallic core, although certain models actually are consistent with or give a structure that is consistent with observations and yield a series that does have a metallic core, although we sort of tend to disregard those. So as I mentioned, the chondrites contain a lot of water, structural water in minerals, and volatiles that are in the minerals themselves, as well as in organics that are found in these meteorites. So the CM chondrites, in this particular case, we're looking at this QUE chondrite, which I think QUE stands for Queen Alexandra. Is it? Well, it's a place in Antarctica, essentially, where this meteorite was collected. The M over here stands for matrix. So within the matrix itself of these carbonaceous chondrites, you find a lot of serpentine. So the C over here stands for chondrules. The carbonaceous chondrites contain chondrules and matrix. And in the matrix itself, you find these phyllosilicates, serpentine, containing a lot of water. In the chondrules themselves, you find a lot of olivine. So that's a magnesium and iron rich silicate. And what you can often see in these meteorites is that the olivine is being substituted for serpentine. There are these aqueous reactions that happened early on in the lifetime of the solar system that formed serpentine from olivine. And sometimes what you can see is the opposite. You're seeing that serpentine is substituted by olivine. So that means that this reaction might be happening. I also forgot to mention that there's a lot of orthopyroxene as well, which again is a dehydrated silicate. So this reaction yields water. As I mentioned before, 1 kilogram of serpentine yields about 0.13 kilograms of water. So we think maybe this reaction might be happening early on in these bodies, such as Europa or Ceres. So to test this hypothesis, we built this model where we look at an accreted state for Europa, and we assume that it accreted in a homogeneous fashion, and then it experienced some sort of heating. We know that Europa, as I mentioned before, is differentiated. It has a metallic core, and it has an ocean on top. And so at some point, the minerals inside experience heating and release their volatiles. Perhaps Ceres is at a stage where not all the volatiles have been released from the interior. So you don't end up with a Ceres with a metallic core in the interior. But perhaps this case applies to Europa, and we also think Ganymede might be in this state. So that's sort of the cartoon model here. And we will move on. So how do we actually solve this problem? So I won't go into the particular details of this equation, but essentially we minimize the Gibbs energy. Minimizing the Gibbs energy means that we will get a phase assemblage at equilibrium. We can predict what the minerals should be at equilibrium. So for that, we need temperature, pressure, volume, and entropy, and we need some knowledge about the composition of the system, chemical potentials, and so on. And we solve for mass balance. Now, this can be a difficult process if you do this by hand. Traditionally, people used to use things like thermocalc to do this sort of work. So thermocalc gives you essentially the phase assemblage or the minerals at equilibrium points at certain pressures and temperatures. But we wanted to speed this up and calculate the Gibbs energy or minimize the Gibbs energy for many points in time and at different pressures and temperatures. So we use a program called Perplex, for which we have what we think are good thermodynamic data. There are always limitations in our thermodynamic data and improvements that we can make, including thermodynamic data related to fluid compositions. And that's something that we're working with Mike Brown for. We're trying to understand what fluids might exist at certain pressures and temperatures, and what the densities of those fluids are. So crucially, we need things like the Helgeson-Kirkham-Flowers equations of state and parameters to understand the compositions of fluids at various pressures and temperatures. And so this is the toy model again. But in this case, what we've done is discretize the interior of Europa from the surface down to the very interior into a series of little boxes. And so as these little boxes experience pressures and temperatures that differ from each other over time, then perhaps they release volatiles, perhaps they absorb volatiles. This is something that the Gibbs energy minimization program does for us. And so we eventually reach a state at which the interior segregates its metallic core And that's where we decided to stop the model. Because we don't know what the upper temperature limit is for the interior of Europa. We sort of have a limit or a temperature constraint based on the fact that the interior is differentiated. And we more or less know the temperature at which the interior of Europa differentiated. It's the temperature of segregation of metallic iron from silicate. And we considered various initial bulk compositions for Europa, including 2 different chondrite compositions, one composition based on what might be available around Jupiter when Jupiter formed. This was a really simple Monte Carlo model for which the priors were modified based on what we think was around Jupiter at the time, based on some literature. And then an artificial composition based on CI chondrites, but fixed to a particular redox buffer. And so this is what the models look like on the whole. So this is what Europa's interior produced in terms of volatiles released from the surface down to the interior, to the very center of Europa. So we're starting from essentially the surface up there down to 8.4 or so gigapascal. And so what this plot on the left shows is essentially a very crude phase diagram for where the these colors over here just show the points at which minerals such as serpentine dehydrate and release volatiles. So you can do an integral beneath this curve, and this solid curve over here just represents the temperature at which iron sulfide segregates from, or rather the temperature at which iron sulfide melts. And that is the temperature of segregation of a metallic core in the interior of Europa. So if you add up all of these little colored boxes over here, you can find out how much, what mass of volatiles is released through these reactions, dehydration reactions in the interior. And so this plot on the right then shows the corresponding density, change in density as we dehydrate the interior. The density in the interior also increases for the most part. And overall, this is what this looks like. So over here, we're just adding up all the fluids released, including water, carbon dioxide, and so on. So what is actually happening in these models? So these 2 plots just show the changing mineralogy at specific pressures in the interior. So I can show you the changing mineralogy at all the different pressures within the interior, but just to simplify things, we'll just look at a couple of distinct pressures. So from left to right, you're increasing the temperature. In the top plot, we have CI chondrite, an initial composition of CI chondrite for Europa, and in the bottom plot, we assume that Europa formed out of CM chondrites. And so what we see over here is, for example, antigerite is a serpentine mineral containing quite a bit of water, and it's stable somewhere between 400 and 800 Kelvin at 3 gigapascal. And as you increase the temperature, then it destabilizes and transforms into more dehydrated minerals. And so this orange field over here at the bottom just shows the total amount of fluid released from the interior as a result of these reactions. And what we see is that the phase assemblage in the interior changes depending on whether you start with a CI chondrite composition or a CM chondrite composition. And so these are the main volatile releasing reactions that we found. I mentioned the dehydration of antigerite into forsterite, I should mention that another really important reaction was the destabilization of carbonates such as magnesite, which released vast amounts of carbon dioxide. So these are just a few examples and maybe the most important reactions that we found. So we also computed the solvents that were released from the interior. Water is not the only solvent produced in these reactions. We also found that, as I mentioned, carbon dioxide can be released from the interior. It reaches a state in which carbon dioxide is so much more abundant than water at at high temperatures, that carbon dioxide itself becomes the solvent and carries the solutes with it. And so there are other molecules, perhaps some of these maybe you might think of as possible biosignatures. I was chatting today about possibly using methane in conjunction with carbon dioxide as a biosignature for exoplanets, but we seem to be producing methane and carbon dioxide through an abiotic geologic process. So this is something to be aware of. There are geologic processes that can lead to the formation of these volatiles. But most of what we released was water. So if we add up all the mass, so this just shows the total mass for each of these scenarios that we tested. We also played around with whether we could retain water in the interior of the mantle over time, or if we extracted the full amount of volatiles released as free fluids. So if you add up the total mass, it turns out that for certain starting compositions, you can easily form Europa's present-day hydrosphere. So we exceed that mass or that volume by about 3 times. So Europa's present-day hydrosphere is about 4.8 times 10 to the 21 kilograms, more or less. But we exceed that by quite a bit, perhaps even 10 times more. And so this is just a breakdown of what those volatiles actually are in sort of the elemental makeup. Most of it is just water, hydrogen, and oxygen. But the third most abundant element is carbon, mostly in the form of carbon dioxide, but also a tiny amount of methane. There's also calcium, sulfur, and all these other elements down here. And so these mainly form part of the solute makeup. And so we can start to put a picture or get an idea of what the ocean composition of early Europa might have been like if this was the process under which the ocean formed. So these figures here just show the composition of the ocean from the surface down to the seafloor. So this solid line at the top just represents a 5-kilometer ice shelf, and the dashed line represents a present-day 30-kilometer thick ice shelf. And so what we're seeing in each of these graphs is just the ocean column composition. So in the top left, we have dolomite and gypsum are stable minerals within the interior of the ocean. These are thermodynamically stable and precipitate. And so we have a prediction for the composition of the ocean and the thermodynamically stable minerals within the ocean column. So on the top right, we have the solutes in the ocean, the dissolved components. And what we see is that the most common solute is carbon, mainly in the form of carbon dioxide. Bottom left, we have the pH of the ocean. We've seen that for all these various compositions that we've tested, the pH is actually mildly acidic. So again, assuming that the process for forming the ocean was dehydration or devolatilization of the interior, as the interior differentiated. And we also have the redox potential. So we have a sort of redox gradient. Although the interior is relatively reducing, in this case, a little bit oxidizing, it becomes more reducing as we reach the surface. From the seafloor to the surface, it seems like the composition changes. And this is just to put it a little bit into context. So Europa's ocean is much deeper than the Earth's ocean. But I was reminded of, in the Earth's ocean, we have a carbonate compensation depth below which carbonates are not stable, they don't precipitate, and carbonates are in solution. So in the Pacific, it's at about 45 kilometers in depth, whereas in the Atlantic, it's somewhat deeper. But essentially, down here in the Earth's ocean, we have no carbonate formation. That's why you don't tend to find carbonate fossils that are from really deep, deep. So if you have precipitation of or your organisms that contain carbonate skeletons die, if they end up sinking to the seafloor, they end up dissolving. But we don't see that in Europa's interior. For Europa's interior, dolomite in this particular case, dolomite is a calcium magnesium mineral. Dolomite appears to be stable throughout the ocean column, but so is gypsum. And so these tables here just summarize the minerals that we think would precipitate at the bottom of Europa's ocean. And so for these different starting compositions, we have different thicknesses predicted that might precipitate at the bottom of these oceans. Mainly they consist of, as I mentioned, gypsum and dolomite. For this accretion mix starting composition, we have other minerals, including pyrite. And so we have a prediction for the thickness of that ocean sediment layer and the density of that layer. And at the same time, what I didn't mention was that these volatiles that make their way from the interior of Europa into its seafloor actually are quite CO2 rich. And in the case that Europa is made up of CI chondrites, then you end up exsolving around 270 bars of CO2, which is an incredible amount of CO2. We don't think this would hang around Europa's environment for very long. We don't think an exosphere and an atmosphere would form around Europa for very long at all. Perhaps this was an early pulse of CO2 into Europa's exosphere shortly after it formed, shortly after it differentiated. But in some cases, we form less carbon dioxide that we have to somehow get rid of because Europa doesn't have that carbon dioxide today. So we were thinking about what to do with that carbon dioxide. Could early Europa really have outgassed up to 270 bars of CO2 to space? So this is an upper limit based on the compositions that we tested. But I should note that there's some precedent in the literature. So there's some work showing that Mars could have outgassed 250 bars of water and 55 bars of CO2 shortly after accretion. And there's some older work showing that Triton could have outgassed about 160 bars of CO2. So this is in the same realm of, the same order of magnitude. Essentially, you have to get rid of a lot of volatiles early on. So there are alternatives, though, to where that carbon dioxide could have gone. So carbon dioxide could have been sequestered as clathrates in the ocean. So if you don't know what clathrates look like, this is a basic structure essentially they're like little cages of water molecules with a guest species within the cage. In this case, carbon dioxide is a possible guest species within these structures. And perhaps that carbon dioxide could have been retained early on and is being released today. So there are some tentative plume detections at Europa. There are independent studies that have looked at these possible plumes, which may or may not exist. There's some controversy as to whether these plumes actually have been seen. Okay, so are clathrates potential reservoirs of this primordial carbon dioxide in present-day Europa? So we calculated the stability of carbon dioxide clathrates. It turns out that they would tend to sink in the ocean. So what this plot shows is, again, the ocean column, pressure on the y-axis, and increasing density on the x-axis. So methane clathrates would tend to float to the top of Europa's ocean. And so we can look at the density curves of different fluids under Europa pressure and temperature conditions. So this is some work that actually comes from UW. And that's from Steve Vance's work. I don't know if some of these need updates. We were also chatting about using the ammonia water system, and that would bring down the density of the ocean fluid as well. And then perhaps we'd see different behaviors for different clathrates. Maybe you'd cause clathrates to sink to the bottom or float to the top, depending on the density of the ocean fluid. But in most cases, we saw that carbon dioxide clathrates would tend to sink at towards the ocean seafloor, because carbon dioxide clathrates are more dense than the surrounding liquid. And only in the case where Europa's salinity was quite high, containing, for example, 10 weight percent magnesium sulfate, then we would see the carbon dioxide clathrates floating to the top. So clathrates are a potential sink for carbon dioxide, and perhaps they could reside at the bottom. And so if we actually add up all the carbon dioxide that we outgassed, we calculated that they'd form a 3 to 77 kilometer thick layer at the seafloor, although that would not be a stable configuration. So for reasonable heat fluxes for Europa, essentially the layer would equilibrate to about 500 meters, a 500 meter thickness thick layer at the seafloor. So that is potentially there, but you still have to get rid of a lot of carbon dioxide. So let's take a look at the plumes again. So that's what we think a plume looks like. This was detected by the Hubble Space Telescope in some recent work. So you can essentially do a calculation of how much water and carbon dioxide you can lose over time. We have some numbers for what we think these plumes are essentially behaving like. We think they reach a height of about 200 kilometers, and we know more or less a mass ejection rate. And so if we just plug in the numbers, essentially you can lose about 1 to 24% of the ocean's present-day mass over 4.5 billion years, which is substantial, but it's still not enough to lose water through this mechanism over 4.5 billion years. You have to lose more water early on. So perhaps early outgassing of carbon dioxide could have led to a runaway greenhouse, and maybe there could have been more hydrodynamic escape of hydrogen and yeah, essentially of hydrogen early on. So essentially, you have to lose a lot more volatiles early on in Europa's history. Okay, to summarize and conclude the work on Europa, I'll later talk about Ceres briefly. So from these theoretical models, we've essentially been able to form an ocean on Europa without sort of invoking delivery of volatiles later on, assuming that Europa was formed from carbonaceous chondrites. We constrained the composition of the ocean. I showed you some ocean columns looking at the changing composition of the ocean from surface to seafloor. In all cases, we found that sulfur was more abundant than chlorine. Calcium was more abundant than sodium or magnesium. However, we found that carbon was more abundant than everything else apart from water. So, as I mentioned, the composition of the ocean is depth dependent. It changes with the stability of different minerals throughout the ocean column as a function of pressure and temperature. So I didn't mention some of the observations that we have for Europa's surface. We've observed some chloride minerals on the surface of Europa. This is also done by the Hubble Space Telescope. And although we've seen that sulfur concentration exceeds chlorine concentration in the ocean, we've seen that the chlorine concentration increases as you move up to the surface, from the seafloor to the surface. And so perhaps this is why we're seeing chlorides at the surface of Europa, because maybe these are picked up by the ice-ocean interface more easily, because chlorine is more abundant near there. But of course, we have to carry out the freezing ocean models to figure out whether chlorides are incorporated into the ice more readily than sulfates. So we found a more relevant role for carbon dioxide, or the more important role than previously recognized. These are just some speculative points over here. Perhaps carbon dioxide could be a source of early oxidants for life. Carbon dioxide is used by methanogens. So if there was a big or a large pulse of carbon dioxide early on, could that have been used by life? Perhaps the carbon dioxide could be retained today as clathrate hydrates. Something I didn't talk about, but also it relates to work that has been carried out here. Perhaps carbon dioxide could be in the form of high pressure water carbon dioxide phases, and perhaps the destabilization of these phases could lead to activity. Perhaps the carbon dioxide released from clathrates or high pressure phases could then promote some activity on the ice shell of Europa. Perhaps this is like a seltzer ocean where you shake it up sometimes and carbon dioxide just exerts pressure at the base of the ice shell. And so maybe you get geologic activity as a result. And so finally, we predicted a seafloor sedimentary layer of low density, which I think this is within more or less what Europa Clipper could actually resolve with its gravity science instruments. So this is our prediction. Perhaps this is wrong, but this is testable. We think it's testable by Europa Clipper. So we have to think about what effects this sedimentary layer would have on Europa over time, and whether there's some recent work also looking at volcanism on Europa's seafloor. So we want to understand how the sedimentary layer could have interacted with volcanic activity. How am I doing for time?
5 minutes.
Okay, I'll wrap up really quickly with some of these results from Ceres. Okay, so Ceres is a possible ocean world. We have really recent activity visible on the surface of Ceres. So Ahona Mons over there is less than 170 million years old and contains some salts on the surface, some sodium carbonate. Cerealia facula over there is extremely recent. It's less than 2 million years old and contains high concentrations of sodium carbonate and some form of sodium chloride hydrate. We think this is cheating, really. We think this was remobilized relatively recently. This is not some sort of endogenic activity that happened recently. That might have been because it looks like a cryovolcano, so perhaps it is a cryovolcano. But we think this was just remobilized by an impact because it sits right in the middle of Okator crater in Ceres. Okay, so we carried out a similar model for Ceres. And in this case, we were interested in retaining some of the fluid in the interior of Ceres's mantle. And you've seen this sort of plot before, but what I'll show over here is that for these different starting compositions that we tried for Ceres, and we tried a lot more for Ceres than we did for Europa. So at discrete points in time, so 100 million years after formation, a billion years after formation, and so on until more or less the present day, we get changing density over time. So these colors just represent changing bulk density of the mantle of Ceres over time as temperatures change in the interior, and you get the same sort of phase assemblage changes. So minerals dehydrate and rehydrate, and the density of that mantle changes over time. So with all these starting compositions, essentially we found a few cases in which the mantle density that we predicted actually coincides with the constraints that we have from spacecraft. And so again, we can calculate the fluids produced through this process. In this case, what I'm showing on the left is what's happening at 50 megapascal. And on the right, we're seeing what's happening at 100 megapascal. And there isn't much of a difference. In this case, the changes in pressure aren't that huge within Ceres. And so the different fluid compositions change a little bit, but not as much as we see for Europa. And what we see is that with increasing temperature from left to right, we increase the amount of sodium and the amount of carbon dioxide, which is a cool coincidence because we see sodium carbonates on the surface of Ceres. And so what I should point out is this solid line over here represents the pressure temperature profile within Ceres in the present day. So at 50 megapascal, it's quite cold. At 100 megapascal, it's quite hot. So it's a steep gradient. Whereas this dotted line over here shows the essentially the geotherm, the pressure temperature profile within Ceres shortly after accretion. Shortly after accretion, the composition of fluids would be relatively or quite similar from surface to interior, but in the present day, you'd have sort of a particular composition near the surface and a completely different composition in the deep interior. And so, again, this is the same sort of graph where we look at the changing minerals with increasing temperature, and you see that the different minerals dehydrate and rehydrate. And so I just thought it was a cool coincidence to see that we predict some of the minerals that have been seen in certain meteorites. So this Alma-Ata Sita meteorite is a was a meteorite found in Sudan. We've studied it extensively. It contains some minerals such as serpentine and high temperature minerals such as tremolite, which we predict to form in our models. And so this phase assemblage signifies that this meteorite experienced some form of dehydration. We don't think that Alma-Ata comes from Ceres, but it almost certainly experienced high temperatures and high pressures similar to what we think Ceres experienced. And I'll just conclude and summarize the work that we did for Ceres. Overall, we found that we can't dehydrate Ceres entirely. If we dehydrate Ceres entirely, then its density is too high, and it doesn't fit with our observations, particularly from the Dawn spacecraft. So we require some fluid-filled porosity in the interior to explain its density. We think that some of the minerals are a little bit like the Alma-Ata meteorite. So we have a hand sample of some sort of body that experienced those conditions. And these are just some random thoughts I had towards the end. So if you release volatiles from Ceres, does that mean that you affect the surface of Ceres over time? Do you get like some sort of interesting geology happening, or perhaps you're getting rid of craters or crater morphology on the surface? That's something that could be fun to quantify. And this is maybe something of an open question. Are oceans generated through these metamorphic processes prevalent out there? Perhaps exoplanets also generate oceans through this sort of process. And there's a typo there, but are they distinguishable from other types of oceans? Would we see that in some sort of signature? Say accreted oceans, could they have a different signature to oceans generated in planetary interiors? I think I'll leave it at that. There's a fun picture of the Europa Clipper mission that's supposed to launch in 2024 to visit Europa and test some of these ideas. So thank you very much. And
Questions?
Thank you very much. Before I take questions, I just wanted to make a couple announcements I probably should have made before. So we are going to be taking Mohit out to dinner tonight. So if you are interested in that, please come find me after this talk, or you can also email me. We'll probably leave around 6. Number 2 is that the next 2 seminars we have are all going to be all virtual. So as much as it's been wonderful to be here in person, the next 2 will be online. So be aware of that. So we won't be back here in this room for 3 weeks. So anyway, those are my 2 announcements. So please go ahead. Yeah, questions. Yeah.
Hi.
Do I have it right that first of all, thank you for using a current version geochemical code to follow the consequences through on this planetary evolution. The question is this a purely magnesium mantle? No iron?
No, it does contain iron as well. Yes.
And how do you start the iron magnesium ratio?
So we used we sort of parted from using carbonaceous chondrites as our starting material. So the magnesium to iron ratio or iron to magnesium ratio is fixed to those particular starting compositions. Then changes happen. Perhaps you end up putting magnesium into solution more readily than iron, or you put more iron into solution, depending on the redox state. And so that ratio can change in the interior of these bodies over time. Does that make sense? Or?
Was there magnetite being produced in your serpentine dehydration?
Yes.
It was. Okay.
Yes.
And HKF is a framework
Yes.
rather than a particular method. And so what did you do about what choices did you make on activities?
Okay. So I'm going to anticipate this. So this is an extension of HKF. We've had discussions about the deep earth water model before and how it may or may not be adequate. So I'm using the deep earth water model, which,
That gives you the standard state for the, but for the gamma,
yes,
the gamma dot.
that's right. So this is for the coefficients, sorry, essentially the gamma. But so the perplex database has an extension of the deep earth water model, HKF parameters, and so on, that go up to 6 gigapascal. They may or may not be entirely accurate at those pressures. That's something that you need to help me with. But for our purposes, we were talking about this a little bit earlier. When you play this game of silly numbers, as I do, then you may get silly numbers at the end. But to us, I've tested, for example, the deep earth water model water density against the sea freeze water density, and the differences are within 3%, which are a lot in the lab. But for me, that doesn't make a huge difference. If I end up producing 270 bars of CO2, that, you know, it doesn't matter whether I produce 270 bars of CO2 or 100 or 50. It's still a lot of CO2 I need to get rid of, if that makes sense. For planetary science applications that I'm currently carrying out, those small differences in water density or activities don't make a huge difference. Overall, the message is that you end up forming these massive amounts of volatiles. Yes.
There was a dramatic difference in the phase abundances at depth for CI and CM starting materials. And one had a lot of olivine and it doesn't have any olivine. And I thought this is very strange because the CI and CM were major elements with the same composition.
Yeah.
Except for carbon and water. And it's not that much of a difference between them. So is this physical? Is this real? Or, I mean, so much, you had a huge amount of talc on one side and something else with no olivine. I was imagining that all these bodies had some big peridotite body somewhere in the middle.
Yeah, that was surprising to me as well. So I don't know why that is actually happening. But we think the model is well calibrated. What we'd like to do is to experimentally heat up some chondrites and see whether this is actually happening at those pressures and temperatures. So there's some old work by Carl Agee heating up CV chondrites, and they find a lot of olivine, and they go up to the melting curve. Yeah, essentially the solidus of CV chondrites, and they do find a lot of olivine forming before the CV chondrites actually melt.
Yeah, because the solar composition and the oxide conditions is all we know. So it's almost the inevitable end product.
So
Usually.
yeah, and I don't know why that is happening, but I suspect that it has to do with the volatiles actually being released. So I don't know how to carry out those experiments where we're allowing volatiles to be released from a chamber. How do you do that safely, like, without causing some sort of explosion or hazard? Because the amounts of water and carbon dioxide released actually affect the redox state of the rock as well. So maybe this is why you're getting olivine in some chondrites and not in others. I don't know what the answer is. Yeah. Oh, sorry.
So Vesta is differentiated and it's much smaller than Ceres. Why would that be the case that Vesta is in Ceres is not?
That is a good question, and something that people have been thinking about as well. Some people have thought of Ceres as a outer solar system body that has migrated into the inner solar system, and that's why maybe it has a lot more water and hasn't experienced as much heating. That is one possibility, but I'm not a dynamicist, so I can't really comment on those things. That you had a
Well, yeah, a huge number of fraction of bodies formed when there was still aluminum 26 in the solar system. So it formed early, they melted. So, maybe Ceres was formed a little bit later,
That's another explanation. You had the short-lived radioactive elements still live when Vesta formed. So iron 60 is another one that would have contributed quite a bit of heat within Vesta early on, and maybe that contributed to the differentiation. Whereas when Ceres formed, maybe those elements had already decayed.
Last question.
Okay, I'm actually have more than one question.
All right, pick your favorite.
Okay, well, I'll pick my two favorites. I have three. So most people, when they're talking about life in Europa, they talk about this hydrothermal system that exists on the seafloor. It seems like if your result is true, you've got kilometers of gypsum down there, and what isn't that going to preclude life, at least that's frequently discussed with this body?
Maybe. So there's some work also looking at whether you can fracture the seafloor of Europa and allow percolation of fluids to the interior, so you can have some serpentinization occurring, and maybe that can help methanogens. But that sort of work is like the current thinking is that it's very difficult to fracture Europa's seafloor and to get permeation to the interior. So maybe sediments, low density sediments that are porous, may actually be useful for life because you can get circulation of fluids through those sediments. That is one way to look at it. And that would go about the problem of fracturing the seafloor and allowing fluids to permeate.
Okay, you didn't have a time-dependent model, but because you're dealing with just equilibrium cases, but the series, how long are you thinking an ocean lasts?
So this is a question for Julie Castillo, actually. But it's tens of millions of years. That was the order. Not particularly long
Right.
in sort of context, but another option is that there are still fluids in the interior, simply because they would be in in liquid form. It wouldn't be in icy form within the mantle. We're reaching temperatures where the ice should be melted. Then it isn't really an ocean, but there are still fluids within pores, perhaps interconnected or perhaps not.
All right. Thank you very much, Willie. Let's thank our speaker again. See you all in 3 weeks. Yep, and I would say